So yeah, I'm going to talk about the analysis of organics in solar system materials. And there's four main points I want to get across today. The first is, what are the questions we're trying to answer by analyzing these materials? The second is, what are the analytical techniques that we have? What types of analyses do we do? The third is, what samples do we have access to in this area of research? And then the fourth overall is the challenges that we're facing when we try to do these analyses. And so here's a cartoon of astrochemical processes that happen in a variety of environments. Everything from the diffuse interstellar medium all the way down to planetary surfaces. And in all of these different environments, there's chemistry going on. There's reactions going on and organic chemicals being formed. And in each of these environments, we have different tools available to study the chemistry. And most of what we heard yesterday was looking at this area of the cartoon and remote observations and laboratory studies of analogs and simulations. What I'm going to focus on is this part here, where we can have actual samples of solar system materials, bring them into a lab on Earth, and analyze them to understand what's there. And so that includes samples retrieved from solar system bodies through sample return missions, and also samples that are delivered naturally to the Earth, like meteorites and interplanetary dust particles. So we're kind of accessing a different area than what we heard about yesterday. And the questions that we're trying to answer when we're looking at organic compounds in these materials are really, what was the origin and distribution of complex organics in the early solar system? So that ties back to, what was the chemistry like when the solar system formed? And then also, what's happened since then? What can studying organics in these materials tell us about the chemistry that's happened in the last 4.5 billion years within some of these primitive bodies and solar system bodies? And so when we analyze solar system samples, we often see a complex mixture of organic compounds. Here's a piece of the Murchison Meteorite. It's been mentioned a couple times already, I think. When we look at the organic inventory there, we see a very rich and complex mixture. Many different types of compound classes present. Over 1 million different separate chemical formulas have been seen in the Murchison Meteorite. So it's a very rich suite of organic materials, very complex. And this is a primitive material that probably tells us a lot about it's a bit of a snapshot of the chemistry of when the solar system formed. So we have signatures of early solar system chemistry, but these parent bodies that the materials came from have also experienced processing in the last 4.5 billion years. So some of these asteroids have seen aqueous alteration with liquid water. You've had thermal alteration with heating. And so in addition to that primitive material that was there when the solar system formed, there's these effects overprinted on it of processing histories. And so we try to understand that as well. And then this has also been mentioned a couple of times. This delivery of extraterrestrial organics to the Earth helped to provide ingredients that were present when life formed on the Earth. And we don't know the relative importance of the exogenous delivery versus the synthesis on the terrestrial surface, but it's important to us to understand what that delivery could have involved and what could have been delivered that way. And here's an example. The specifics of this aren't exactly important, but it's an example of how studying different kinds of compounds might help us to understand chemical formation pathways. So here's some potential reactions that could lead from interstellar material, some of the things we heard about yesterday and earlier, leading all the way to some more complex molecules like glycine and methylamine, which have been found in meteorites. And so by trying to understand the abundances, the isotopic ratios of all of these different compounds in different environments, we can try and understand if these pathways were happening, in what conditions, in what environments. How did you get from the simple interstellar molecules to the more complex organics? And some of this might have happened in parent bodies in the solar system. So how do we try and answer these questions? We're trying to understand the organic inventory. What do we actually look at in the lab? What types of analyses do we do? So one thing we're very interested in, obviously, is the chemical distribution. What chemicals are there? What compound classes are present? And their absolute and relative abundances. Abiotic chemistry tends to be very diverse. When we're looking at amino acids in meteorites, amino acids in biology on Earth, we use only about 20 amino acids. When we look at meteorites, we see basically every structure you can draw. Over 90 have been identified. There's probably many more that are just impossible to separate and identify. So we're interested in looking at those absolute abundances, but also the relative abundances. Do we see straight chain dominating over branch chain? Do we see certain structures that are more abundant than others? And what can that tell us about the formation mechanisms that led to these molecules or their preservation over time? We look at isotopes, and that's been mentioned a couple of times already. But in particular with the organics, we're often looking at the carbon 13 to 12 ratio, nitrogen 15 to 14, deuterium to hydrogen. And again, that helps us to understand the formation environments and maybe the formation mechanisms that led to what we're seeing. And also we can use that to look at connections between molecules from different compound classes to see if maybe there's a we can figure out what the precursor was for the molecules that we're seeing. And we also look at chirality, and this is in particular for amino acids, but also for other chiral molecules that exist in enantiomeric mirror image forms. We know that life on Earth uses homochirality, pretty much uses the left-handed amino acids for life, but abiotic chemistry should produce racemic mixes, equal amounts of the two. In some cases, we actually see excesses of the L in meteorites, and so we're trying to understand where that excess came from, how big those excesses can get, and whether the delivery of these chiral molecules to the early Earth may have played any role in how biology chose to use homochirality. And in order to do these analyses, we're often looking at soluble organics, and this is what I'm going to focus on mostly because this is what my lab does. Here's just some of the compound classes that are targeted in analyses of this solar system materials in lab analyses. There's also a lot of insoluble organic matter. Quite a bit of the carbon in meteorites is tied up in this kerogen-like macromolecular material, aromatics with small aliphatic chains and other compound groups hanging out in there. It's can be a little bit harder to analyze, or you analyze it by different techniques. So I'm going to focus mostly on the soluble organics. And so in order to target all of these different compound classes, it's actually very tricky. You might think, oh, well, we know how to analyze amino acids on Earth. We know how to analyze aldehydes or alcohols or PAHs in terrestrial samples. There's EPA methods for a lot of these. So why can't I just use those when I'm analyzing a meteorite or an extraterrestrial sample? And it's really has to do, there's several reasons. One is, like I showed you with the Murchison Meteorite, these are very complex, rich suites of organics. And so there's a lot of potential interferences from all of the other molecules that are present. If you're targeting looking at amino acids, you have to worry about interferences from other compound classes. So we have to do a lot of workup to remove the compound classes or salts that can impact your separation or derivatization or your detection methods. These are molecules are often present in very low abundances, trace levels, and so that can be very tricky as well. We often take techniques and instruments that exist and we tweak them to improve our sensitivity at the cost of precision. So often we're willing to suffer bigger error bars than you would be able to do when you're looking at terrestrial questions, but we're able to make that exchange in order to gain more sensitivity. These are really complex mixtures, and like I said, abiotic chemistry tends to be very diverse. You can get all possible isomers and enantiomers present of a certain molecular formula, and in order to try and quantify and understand those, you really need to spend a lot of time developing your separation techniques and your identification techniques. And so we often will have chromatographic runtimes that are much, much longer than our typical, because we really need, we're willing to give up our time in order to get better separation. We always have to worry about contamination. A lot of the molecules that we're looking at are very present in the biosphere on Earth, and so we always need to understand how we can be sure that what we're looking at is indigenous to our extraterrestrial sample and is not the result of contamination from Earth, from either collection or curation or workup. And finally, all of these techniques usually, sometimes someone gives us a sample and says, tell us all the organics that are present in this. And that's really tough to do. So we usually do targeted analyses. We say, we're going to look at this time in this sample for this compound class, and we optimize our method for that. But that does introduce some biases, potential isotopic fractionation, that you really need to understand how the whole workup method that you do affects your results. And so, and usually, the sample is way more precious than our time. So it's worth it to us to spend 2 years developing a method and then applying it to maybe a handful of meteorites. Because these meteorites, these other extraterrestrial samples we have, they're a limited resource. Our time isn't as much so. And so there really is a lot of method development that has to happen before we even touch these precious extraterrestrial samples. And here's an example. I'm going to focus most of my examples today on amino acid analyses because that's an area that our lab has done a lot of research in, although we've done some other compound classes, well, more and more compound classes now. But if we want to look at amino acids in an extraterrestrial sample, we start by crushing the sample. So here's an example of taking a little bit of meteorite, crushing it in a mortar and pestle. We do a hot water extraction because we know that our target molecules are soluble. We usually split the extract in half and we'll acid hydrolyze half of the extract. That helps to liberate amino acids from bound forms or from precursors. We do desalting. That helps to get rid of some of those interferences. If we want to do the characterization, like looking at abundances and distributions, we'll do a certain type of derivatization and use liquid chromatography with fluorescence detection and mass spectrometry. If we want to do isotopic measurements, we have to do a different derivatization, and we use gas chromatography, again with mass spec and isotope ratio mass spec. So we have a whole flow chart that took us a long time to develop. Contamination control is very important. We bake out all of our glassware, our ceramics. We're very careful with our reagents to make sure that they're clean. We do a lot of blanks and standards to make sure we really understand all of the contamination background because, again, amino acids are everywhere. So this is an example of the type of workup that we have to do in the lab to get analyses data. So now I want to talk a little bit about the types of samples that we have available for these lab analyses, and I'll take you through some examples of the analyses we've done and the data that we've seen. So we do a lot of work with meteorites. Those are great. They're free sample return. They get delivered to Earth, all the time, and that's wonderful. The other nice thing about meteorites is they come from a variety of different parent bodies in the solar system, and so they help to give us diverse samples of different environments. Stephanie was just talking about with comets, you only have 1 or 2 measurements. You really wish you knew more. Meteorites give you the diversity, but we don't know what their parent bodies are for the most part. So we have this diversity, but we can't necessarily tie them to specific parent bodies. So that's a challenge of meteorite work. So that's where sample return missions come into play. With sample return, we get these great samples. We have a lot of context and information about them. They come from specific bodies, and so they can help us to answer specific questions. And so I'm going to talk, we have the lunar samples that were returned by the Apollo missions. We have cometary samples, like Stephanie mentioned, with Stardust. And then we have asteroid sample return, a couple of missions in progress right now to bring back some asteroidal material. And so I'm going to show you some results from all of these types of analyses. Meteorites also span a range of scientific value, I would say, or contamination at least, as far as documentation. There's professional meteorite hunters who will go out and collect meteorites. Those aren't necessarily the best documented or the most clean, useful samples for us. In the middle, you might get lucky with an observed fall of a meteorite. This was the Almahata-Sutta meteorite that was observed to fall, and so there was a scientific expedition with students put together to go out and try and collect and find those meteorites. So that was better documented. There's also what's the most useful source of meteorites for our research is ANSMET, the Antarctic Search for Meteorites, which is a joint NASA, NSF, Smithsonian group. They go every Antarctic summer, so they actually should be gearing up to leave. I haven't looked at their blog yet this year, but they should be leaving in the next couple of weeks. And they go down and they go to Antarctica, because meteorites fall all over the Earth. So you could collect them anywhere, but there's a couple of advantages to going to Antarctica. For one, in some cases, the rocks on top of the ice are a little bit easier to see, and they're more likely to be meteorites. There's less contamination there than in other places on Earth. And the ice sheets function as a conveyor belt, and so they can collect meteorites from a large area and bring them up against the base of the mountains, so you can get a higher concentration of meteorites there. And so they usually come back with between 200 and 1,000 meteorites each year that are then curated and collected at Johnson Space Center and available for research. It's a very, very valuable resource for us. And actually, Danny Glavin, the next speaker, is in this picture here, because he was on ANSMET a few years ago, so you can ask him some questions. So those are the less contaminated, better documented samples. And then here's some examples of the types of blanks and controls that we try to have as well. We have our laboratory blanks to understand contamination from our lab. And when we can, we try and get soil or ice from where a meteorite was collected, so we understand any environmental impact that might have gone into the meteorites. Organic compounds have been analyzed in a variety of meteorites. Here's kind of a simplified chart showing different types of meteorites. There's the irons that you'll see the giant irons in museums, but most meteorites that fall are stony meteorites. And the ones that we focus on for organic analyses are the carbonaceous chondrites, which make up about 4% of meteorite falls and contain a few weight percent of carbon. So they have a higher abundance of carbon, higher abundance of organic materials, organic compounds for us to study. And then those are further divided into groups based on mineral and petrographic analyses. And we think that each of these groups of meteorites comes from a single parent body. So by studying several from CM meteorites versus CVs, we're able to get at some of that diversity of parent bodies and understand differences between them. All of the colored groups here are ones in which amino acid analyses have been reported or have been done so far. So we've looked at a big diversity of meteorites. And again, when Stephanie was talking about diversity of comets, how you want a lot of diversity, that's one of the benefits of meteorites, is we're able to look at this many samples. And so here's an example of why we need to do that. This is amino acid abundances in a log scale, parts per billion. And each of these bars is a different meteorite we've analyzed in our lab. They're grouped roughly so that the ones on the left have seen more aqueous alteration on their parent bodies. The one on the right have seen more thermal alteration, more heating. And the important takeaway from here is that amino acid abundances can vary by 3 orders of magnitude. There's a lot of diversity. You can't just say, oh, we've studied this one meteorite. We know everything about what amino acid abundances were in this material. You need that diversity. And here's another way of looking at the diversity. Might be hard to see, but these are the 5-carbon amino acids. You can draw 23 different isomers and enantiomers of 5-carbon aliphatic amino acids, and you can divide them up based on how close the amine group is to the acid group. And then we've plotted down here those relative proportions of alpha amino acids versus beta, gamma, delta. And again, there's a lot of diversity. Some meteorites are dominated by alpha amino acids, which are the amino acids we use in biology. And some are really almost predominantly the straight chain. And so we think by understanding these relative distributions, it can tell us something about formation mechanisms, formation environments, and processing histories. So meteorites are great. Return samples give us even better contamination and better documentation. So I want to talk a little bit about what we've learned from returned samples as well. Sample return missions, the gift that keeps on giving, because once the samples are here, they're curated and they're stored for many, many years and can be used by scientists who aren't even born yet to analyze, with questions that we haven't asked yet, with instruments that we haven't even developed yet. So they're really useful. We have lunar samples. We have samples of the solar wind, cometary material, asteroidal material, and we may in the future get comet surface material, depending on what happens with the Caesar mission selection. And here's an example of why we need sample return. In situ measurements, like we're going to hear about next with the Mars measurements, those are great. We need in situ analyses as well, but there's so much that we can do in labs on Earth that we just will never be able to miniaturize and fly and be able to do these remotely. So we really need to be able to bring these samples to the Earth. So I'm going to talk really briefly about the lunar samples and the cometary and asteroidal samples. So the lunar samples, when they were returned in the 1970s, amino acids were detected, but there wasn't a consensus on their origins. There were 4 potential sources that were identified. 2 were contamination, either exhaust from the lunar module or biological contamination from the astronauts in the collection process. And 2 were extraterrestrial, delivery by the solar wind of precursors or meteoritic infall. And each of these should produce a distinct signature if you look at structural distribution or variations between samples, and isotopic signature. But at the time, those measurements weren't sensitive enough to be able to answer the question. So 40 years later, we re-examined these, and we found no correlation when we looked at samples that were collected close to the lunar module versus farther away. So we ruled that out propellant contamination. We saw no correlation with exposure to the solar wind as far as abundance of amino acids. But we did see amino acids with terrestrial biological isotopes in them, and also amino acids that are not common in terrestrial biology. So we were able to conclude that the amino acids that were present in these samples were primarily terrestrial contamination, but some contribution possible from meteoritic infall. So this is a really nice example of how all of those different types of analyses, distributions, isotopes, multiple samples can be really helpful. And also why sample return, that you can revisit these samples 40 years later, is good. Stardust, Stephanie mentioned really briefly. This was the mission that flew through the coma of Comet Wild 2 and brought back cometary particles embedded in an aerogel collector. The cometary particles themselves were too small for individual amino acid analyses, but we were able to look at some of the bulk material from the collector and see what we found there. And what we found, the red here is the comet-exposed aerogel versus some controls down here. And we were able to identify cometary amines in this material. We also saw 2 amino acids. The glycine here was present in higher abundances than the controls, and by doing isotopic measurements, we were able to show that there was not terrestrial glycine. So that was the first detection of a cometary amino acid. And the other important thing to see here is the biggest peak was epsilon amino N-caproic acid, which is the monomer of nylon, which was also present in the control sample. And this is contamination from the curation process, from the collector in the nylon bags. So this is why witness materials and control materials are really important. And you can't always eliminate contamination, but you can understand it. The last one I want to talk about, I know I'm running out of time, is just the Osiris-Rex mission, which, as Stephanie said, is approaching asteroid Bennu right now. This is a picture from just a couple days ago. It'll arrive at Bennu next month. It will collect between 60 and 2,000 grams of material. This is a carbonaceous asteroid, and it'll return it in 2023, and we can't wait. It's going to be really exciting because we think it'll be similar to some of our carbonaceous meteorites, but we'll have that context and that information to really understand the history of this sample. And the O in Osiris-Rex stands for origins. One of the goals of this mission is to really understand those chemical origins in the early solar system. We're concerned about contamination. So as they were building the spacecraft, there's a lot of contamination monitoring of the environment. And also on the spacecraft itself, there's little witness plates that sample different locations and different times of the mission. And so when that sample comes back, we'll be able to compare the sample with those witness coupons and understand any contamination background. And my last slide, just to leave up here, is the challenges. I've mentioned some of these. I just wanted to list them here. The challenges we have. There's method development because these are complex samples. There's always, you're maintaining a lab facility, always trying to keep it going. That can be tricky. But curation and contamination are issues we always have to think about. Sample availability. Some of these meteorites, there's only a few grams on the whole Earth, and they're impossible to replace. You have to really think about what material is available to answer the questions we want to answer. And then also sample return missions are great, but they take a really long time. They don't happen that often. So again, we're limited there. So, and I know I'm out of time, so I'll stop there.
I was intrigued several years ago when I read one of these articles about people collecting these very micro meteorites.
Yeah.
And where is the size limit to beyond which they are of no use to you in these types of studies?
So there's a colleague in my lab who's working on improving our techniques to really be able to analyze micrometeorites and also hopefully interplanetary dust particles. So that is an active area of research to work on the sensitivity, again, the cleanliness of the method so you don't overwhelm your signal with background. But we are getting down to being able to analyze individual micrometeorites. That's a good question.
I don't know if this is on. Yeah? Okay, cool. You showed a couple of different slides that showed organic compounds across a couple of different comets. You had a handful of those, and then you had the different C5 isomers across different meteorites. I'm wondering, has anyone ever done a simple correlation analysis between these different organic molecules?
Between cometary and meteorite or across? So we don't have too much of the same data from the comets. We only know about one amino acid that's been detected in a comet. Rosetta detected glycine, as we saw in Stardust. But the bigger amino acids, we haven't found them yet in comets by remote observation or even in the Stardust data. And we think that's probably because of sensitivity limits and abundances that are present. If we're lucky and Caesar is selected as a future sample return mission and we bring back that cometary surface material, we're hoping we can get a little more material to be able to get to some of that, some more of those compounds that are present in such low abundances. So we don't really have enough of the same type of cometary measurements to be able to compare with the meteorites.
Okay, I guess I meant within a simple class, within a single class, within comets, based on all of the different organic molecules that have been seen there. Do any of them correlate with others whenever you go across the different comets? Has that sort of an analysis been done yet?
You have to ask Stephanie more about the cometary stuff, because we don't have too much cometary material for lab analyses, which is my expertise. Stephanie, I don't know if you want to talk about.
This may be a question where I should just chase you down later.
Yes, we can talk more. But yeah.
So as far as doing, there's been a lot of work actually comparing the limited number of comets that we've been able to observe. So at optical wavelengths, ground-based observations, there's been hundreds of comets that have been studied. And they looked at things like whether or not multiple carbon atoms correlate with things like water or cyanogen. So they do like a C2 comparison to CN or things like this. And they see some similarities, but for the most part, all the comets look the same. There's also been a survey that's been done on infrared observations of comets. This has sort of been an effort that's been led by Mike Muma and his group. And they've been looking to see whether or not there's an enrichment in some comets with organics or a depletion of organics in comets, and whether or not that correlates to the dynamic class of objects. So whether they're short period comets versus long period comets. And they're really not seeing any correlation between either class of comets. They do see some enriched comets with organics and some depleted, but again, it's not really class specific. And then in the submillimeter and millimeter, we have about 30 comets that we've actually done correlations with. And I think you saw some of those plots in Paula's talk, right? Where she had sort of the distribution of the abundances of different organics that we've detected. And it's, gives you this percentage, but again, we don't see a variation between dynamic class. So whether or not that's because we're sample limited or not is to be determined.
And we do that type of comparison across the different types of groups of carbonaceous chondrites, for example, the ones that we think come from different parent bodies. We definitely look at correlations between different compound classes and the different parent bodies and the different alteration histories to see what we can learn that way.
Are there any other questions?
Okay, I guess with things like principal component analysis, you can take these big multidimensional data sets and kind of group different things. Has anyone tried that with meteorites to see if they group according to the organic compositions?
I feel like we're just at the point of having a big enough data set. We've been doing, amino acids have been studied a lot, and only in recent years have we even gotten to all of the different carbonaceous chondrite groups. That's just in the last 5-10 years we've done all of those. And now we've also been branching out beyond amino acids to other compound classes, the amines, aldehydes, ketones, other things like that. And we're trying to assemble a big data set as much as we can across different meteorites and different compound classes. We haven't gotten into PCA analysis yet, but I'm hoping that when we get that type of big enough data set that we'll be able to enlist that.
Thank you.